We started a discussion in the previous lecture on the duplexing network, where we can connect two users, one on the left, another user is on the right, by two directional couplers. But what if we have more than two users in the network? Let us consider a T network with n terminals, end users, where we have two end terminals, terminal 1 on one side and terminal n on the other side, and several terminals, several users in between that are tapped into the same T line. Overall, we have n terminals, and each terminal in this network has a transmitter and a receiver. It means that at each station, no matter whether it is an end terminal or middle terminal, we can send signal through this network, and we can receive signal from the same network. Obviously, we have a TEE topology. We just need to figure out how we connect different terminals. As we discussed before, to connect two end terminals, the very left one and the very right one, it is enough to connect them by using a simple directional coupler. But for any middle terminal, we need more. So we connect it by using a T coupler. And T coupler could be constructed by using several different approaches. The most common one is just to use two directional couplers together as depicted here. Indeed, let us consider the situation when we want to transmit from this station, from this terminal. We start with the transmitter and send signal through port 1 of the second directional coupler. The signal, if both directional coupler 1 and 2, we assume that they are 3 dB couplers, meaning that light in two output ports, throughput and tap ports, are split 50% each. So if light enters into port 1 of the second directional coupler, 50% will continue to port 2 and 50% to port 3. That light that continues to port 2 will enter port 4 of the first directional coupler, and then will exit through port 2 and 3 of the first directional coupler. That light that exits through port 3, we eliminate it. We can filter it out. We are not interested in that light, so then forget about it. What will matter, only light that will exit through port 2 and continue in the main T line, and light exiting through port 3 of the second directional coupler will enter port 3 of the first directional coupler, will be split 1 to 1, 50% to port 1 and 50% to port 4. That light that goes to port 4, we will filter it out and cancel it. What will matter, only light that will exit port 1 and continue to the left in the main T line. So what we have here, indeed, when we transmit from this terminal, signal will propagate to both directions in the main T line. Now, what about receiving the signal in this terminal? Let's consider first light going from the left, blue arrow. It will enter port 1 of the first directional coupler, will split 50-50. We will filter out signal going to port 2 and will be interested only in signal going to port 3. That signal will enter port 3 of the second directional coupler and partially will go to port 1 and port 4. That light that goes to port 1, again, we will filter out and cancel it, and signals that go into port 4 will reach the receiver at this station. Now, if the signal in the main line goes from the right, it will have similar situation. It enters port 2 of the first directional coupler, will split 50-50. That light that will go to port 1, we will filter out. That useful signal that goes outside to port 4 continue and enters through port 2 of the second directional coupler. Here signal again split 50-50. That light that continues through port 1, we filter it out and cancel it. And useful signal will go through port 4 and reach the same receiver. So we can see here that no matter from which direction we go, from the left or from the right in the main line, the signal will reach the receiver of this particular station. Now, if we are talking about how much loss we would to expect, right? So if the directional couplers are 3 dB couplers, going from port 1 to port 3, let us focus on blue light. When light goes from port 1 to port 3 of the first directional coupler, there will be loss 3 dB. And then when it goes from port 3 to port 4 of the second directional coupler, we have another 3 dB loss. So overall loss for an ideal coupler without any additional losses is 6 dB. Note that in this system, any terminal can transmit and receive in both directions. Only one terminal in the network can transmit at a time, because signal from any terminal will be received by any of the other terminals. So not to mix signals, therefore we have to transmit only one signal at a time. This type of network, where signal sent from any terminal can reach and will reach all other terminals, called a broadcast network. So the TEE topology is an example of a broadcast network. Let us compute for this T network the losses from terminal 1 to terminal N. That is the worst case scenario with the highest losses between two terminals at two sides, at two ends of the network link. Assume that all couplers are identical, and for N terminals there will be in between N-2 T couplers with the loss of the throughput port for each T coupler. There will be also one DC coupler at the transmitter side with the loss of the throughput port, and one DC coupler at the receiver side with the tap loss there. Mathematically then, the total loss added will be N-2 times throughput loss for T couplers, one throughput loss for the first directional coupler, and one tap loss for the last directional coupler. So total, it will be N-1 times the throughput loss plus 1 tap loss. In the real system, however, there are connectors, and each coupler, directional coupler and T couplers as well, they have two connectors each. If LC is the connector loss, there are a total N couplers, N-2 T couplers and 2 directional couplers, so total it is N couplers. So we have to add 2 N LC to the formula. As we can see from this formula, losses increase linearly with the number of terminals N, right? And there is some constant loss in addition to that. For example, assume we are dealing with ideal 3 dB couplers, therefore throughput loss and tap loss is 3 dB, and the connector loss is 1 dB. The loss increases for each additional terminal by the amount it will be added another connector and another throughput loss, so it will be 3 plus 2, additional 5 dB. So every extra terminal added in the middle will add extra 5 dB loss. Okay, and therefore overall loss scales linearly with the number of stations. On this plot I show 4 cases for this dependence. Those 2 ones for ideal couplers with the splitting ratio 9:1, this line, and 3:1, this line. For the same splitting ratio but adding excess losses of 1 dB, and connector losses of another 1 dB, we will have two more lines, much steeper lines. The red one for the case of 9:1 splitting ratio, and magenta one is for the splitting ratio 3:1. As we can see, if we add extra losses such as excess losses and connector losses, the losses increase more steeply, but the dependence itself, it's still a straight line. Summarizing notes. Losses for transmission between adjacent terminals will be much smaller than losses between terminals far apart, and the worst case scenario would be the transmission losses between two end terminals. We might start with a T network with only few terminals, only few stations, and then add more and more stations as needed. When it happens, losses, transmission losses, will start to increase, right? Because as we saw in the previous example, each terminal connected will add approximately 5 dB additional loss. So receivers in this network must operate over a wide dynamic range to be able to measure a wide range of optical powers. With many stations connected to this network, losses can be very high. And we know that those losses scale linearly with the number of terminals. Therefore, number of terminals connected losses could be too big to get any signal in this network, and therefore n is a good number to consider. So when the number of stations grows beyond 10, T network will suffer significant losses, and signal delivered to very far terminals might not be sufficient to measure, right? If n is larger than 10, normally we would start to look for a different topology away from T topology.